So, good morning. We have discussed about the insulators for the ultra high voltage transmission. Subsequent to that, we have also discussed about various types of conductors which are used for transmission, particularly at EHV and UHV levels, which are of important. The next next topic for discussion is the important and most important component being the towers for transmission, and further we will be looking into the foundation aspects of the tower to a briefing very briefly about various foundations which are being used for the tower depending upon the area, depending upon the configuration of the tower, how the foundations have to be carried out. So, towers are very important for the mechanical strength. They have to carry various insulator configurations, the insulator load, the conductor load, the accessories connected with the insulator and the conductors, the ground wire or earth wire, then its own weight of the steel structure. So, the tower plays a very important role in the high voltage transmission systems. So, the towers and foundations are very important. This figure shows the clearances to be adopted in case for the distribution system, and also the span is very important, taking into the consideration of the sag, the vegetation and various obstacles which could overcome, hard to be considered for the proper design and construction of the overhead transmission or distribution lines. So, as per the international and the national standard, various specifications are laid to see that in case of the rail transport or the river or the normal traffic, what are the minimum clearances to be maintained apart from the electrical clearances for the tower. The span length and the tower height is a very critical while estimating the tower for a particular voltage level. So, this shows the span length. Span length is from tower to tower distance is known as the span length. The minimum clearance is from the ground to the conductor is the ground clearance or the clearances which is termed in the electrical aspect. So, these clearances apart from the electrical clearances, minimum clearances in case of the transportation or the river crossing or the vegetation have to be adhered as per the norms and specification prescribed by the international electricity rules or Indian electricity rules before the towers are being constructed at different locations. So, some transmission facts, this gives the idea of the total height of the tower, brief information for 400, 500 and 765 1200 kV towers. You can just see the for various voltage class, say for a 345 or a 400 kilovolts single circuit, if it is a double circuit, or in case of a 500 kV single circuit or 765 or 800 kV single circuit and 1200 kV single circuit. Two options are given here. One is for the hilly terrain where the land is not planar and the terrain is of uneven in nature in such cases, and for a flat terrain. So, what are the clearances, minimum ground clearances to be adopted? Say for a 400 kV or 345 kV single or single circuit, the height is 125 feet. 125 is approximately 40 meters from the ground level has to be maintained in case of a flat terrain, whereas for a hilly terrain it is 110 feet. So, 110 feet is approximately 32 or 33 meters from the ground level. Similarly, if it is a double circuit, the clearance is 175 feet and 160 in case of the hilly terrain, and for 500 kV single circuit lines it is 135 in case of flat and 120 feet, that is around 40 meters from the ground in case of a 500 kV. So, subsequently for higher the voltages, ultra high voltage ranges, you can see for a 765 or 800 kV single circuit towers, the minimum height required in case of hilly terrain is 135 feet, approximately 40 meters from the ground level, and if it is a flat, it is slightly higher, it is 150 feet, so around 50 meters from the ground level. So, similarly for 1200 kV single circuit, the clearances required in case of hilly terrain is 165 feet, and in case of a flat terrain it is 160 180 feet. So, what are the minimum clearances as mentioned in the previous slide? Example, what are the minimum clearances to be left to be considered apart from the electrical clearances in case of the railway traction or a railway zone where the transmission or distribution conductors are passing near the railway junctions or railway tracks. The minimum clearances to be added for the trains, or in case if it is a river, or in case of a normal traffic, or because of vegetation, the following clearances have to be maintained. So, this gives the reference height, particularly in feet, to be considered for the distribution lines in addition to the electrical clearances. So, in case if the rail tracks, you have to have a 22 feet minimum consideration for the area. Then in case of normal road or the streets 14 feet, then residential driveways, it may be a vehicular traffic movement of 14 feet is to be considered. Similarly, if it is only pedestrian, 8 to 10 feet is normally considered apart from the electrical clearances. So, the places where the water bodies are available and the distribution lines pass on these water bodies, in such cases, depending upon the activity like the steamboat or the boating activity, the clearances have to be maintained anywhere between 12.5 feet a minimum. So, again the activity in agricultural areas, if the activity is around 20 acres of land, then the clearances have to be around 16 feet. If it is more than 20 acres, the clearances adopted is 30 to 36 feet. So, these are all the reference details, height details given as per the international or the national standards, which are to be adhered during the distribution tower construction, so that necessary clearances have to be maintained where the electrical accidents do not occur. So, these are some recommended vertical distances or clearances of the conductors which are above the ground roadways, railways or water surface places where these have to be adhered. So, in such cases the international rules very clearly specify for various voltage levels, the clearances have to be adopted in case of railway tracks or roads or driveways or parking lots or the agriculture activity where the land is being cultivated or the spaces for the pedestrians and the water bodies, and also the public or private land where the activity like the sailboats or so on are being employed. So, these vertical clearances are given depending upon the voltage level up to 46 kilovolts. These are the clearances for 66 kV system. These are the minimum clearances which are to be maintained apart from the electrical clearances to be added to this number. So, for 132 kV, 160 and 230 and so on, the clearances are clearly specified by the national electrical code or the Indian electricity rules wherever the towers are being erected, either distribution or the transmission. These clearances have to be added for the proper clearances, and no accidents could occur in case if the rules are adhered to. So, how are the horizontal clearances in case of domestic buildings, very important aspect, but how it is to be added in case there is a building, consider a building. So, how close could the distribution tower or a transmission tower could be there near the domestic construction, or if the already the domestic towers or the distribution towers or the high voltage towers are existing. So, how far should the house be constructed. So, this gives an idea. This is again as per the international or Indian rules where the minimum clearances have to be maintained. You can very clearly see these are the distribution tower. This shows the insulator string. There will be a swing during the wind or during the vibrations or activity of heavy winds. So, this angle of the swing is known as the phi. So, this phi, the moment of the horizontal insulator that is our suspension insulator to a tilt angle phi, the distance is here. So, this distance minimum should be clearance is x. So, x is the minimum horizontal clearance required for any conductors which are displaced by 6 pound per square feet is the wind. So, when the wind blows, the minimum clearances have to be maintained is x, x corresponds to 6 pounds per square feet inch, which include altitude corrections in some cases. Similarly, y is the actual distance of the insulator string to the constructed house or a residential apartment, where this shows the horizontal or a total horizontal distance from the insulator, that is a suspension insulator to the structure. So, this is very important. The swing angle has to be considered for a particular area. Again, the phi is being the conductor swing angle in degrees under 6 pound per square feet of the wind. SF is this distance which is the conductor final sag at 60 degrees with the same wind pressure, and X is horizontal, and Li is this distance is the insulator string length. Li is 0 for post insulator, because if you use a single rod insulator this could be considered as a 0 or restrained some for equivalent to suspension insulators. So, y is the horizontal, you can see this y is the total horizontal distance from the insulator suspension point. Then delta is the small shift, here you can see the delta, a small shift in the structure deflection. This happens because of the heavy winds or because of the movement of the conductors and the insulator string. So, a deviation in the structure could take place by a small angle delta. So, the delta is a structure deflection angle with reference to 6 pound per square feet of wind. So, these are the minimum horizontal clearances requirement to be made for buildings or the apartments which are constructed nearby the distribution or the transmission towers. So, these distances are clearly given in the international and Indian electricity rules. So, the activity should not be the distances should not be reduced for a particular voltage level. So, similarly, in case of vegetation or a forest area where the distribution or transmission lines are passing, similar clearances have to be maintained, and this shows how the radial clearances required for the vegetation. Again, a similar total horizontal distance have to be maintained. In case of swing, what is the minimum horizontal clearances required for the conductors which are displaced at that particular wind speed. So, a similar arrangement for the vegetation also exists, along with the small angle delta, tilt angle or a shift angle of the entire structure deviation which happens because of the wind flow. So, this have to be considered for the proper functioning of the transmission system. The clearances have to be maintained. So, we have discussed these aspects, but several of the countries including our country, we see several transmission and distribution lines crossing the domestic and the commercial buildings. So, here a care has to be taken not only by the utilities, the public at large have to see and follow the rules which are laid by the electricity authorities and the distribution companies, where a minimum clearances or the right of way which we term it, we will be discussing about that aspect. So, the right of way is the minimum clearances from the mid portion of the tower to the either side have to be maintained, and this right of way is very clearly specified for various voltage levels to be adhered, else there could be electrical accidents because of the conductors coming in contact with the residential buildings or the apartments. So, strictly the utilities public have to be adhered to the rules of the minimum clearances stipulated by the Indian electricity authorities, Indian utilities, or the distribution companies who are supplying the electrical power. So, what are the minimum clearances? This again gives the entire data for the various voltage levels, recommended design horizontal clearances from the conductors. So, the minimum clearances from the conductors at rest and displaced by with reference to 6 pound for square feet wind pressure to other supporting structure buildings other than installations. So, these are again as per national electrical standards and code which are adhered to be followed. So, this data is been given for various voltage levels starting from 33 kV to 220 and further higher the voltages. So, this data is available in the electricity authority websites and also the Central Electricity Authority of the Government of India website, where you have to adhere the minimum clearances as necessitated and as been maintained by the government or by the electrical authority or utilities of that respective area. So, we from the distribution we will move to the extra high voltage or ultra high voltage transmission towers. How to consider the design factors, particularly under steady state. So, what are the parameters to be looked into? So, the maximum allowable that is a bus voltage could be any voltage of transmission, could be 220, 400 or 765 or 800 kilovolts. So, the minimum maximum allowable bus voltage is important factor to be considered, and across the equipment for a given voltage level. So, any specified voltage level for the equipment which is being used at that level has to be considered. The second point is the current density in the conductors. So, what is the current carrying capability, the dimension of the conductor, the diameter of the conductor, and what is the conductor which how much is the current density in that, which determine the cross sectional area. So, this again depends on the resulting temperature rise etc. So, this is very important. Further bundling, what type of bundling has been done? It is a twin or quadrupole or hexagonal or octagonal type of bundling, and particularly per phase have to be considered. Then corona inception gradient, again this depends on the size of the conductor, the surface conditions of the conductor, and the energy for these factors are important for fixing the conductor diameter and number of conductors to be put in the bundle. So, all these are very important. What is the voltage level and how many bundling have to be carried on, what is the corona inception gradient. So, this helps in fixing the conductor diameters and number of conductors, whether to go in for a twin bundle, go in for a quadruple bundle or go in for a hexagonal or octagonal depending upon the voltage level to be transmitted. Next will be the electrostatic field under the line at the power frequency operating conditions. So, the minimum clearances or the minimum electrostatic field which is specified has to be considered for the design aspects. Then further audible noise and the radio interferences. These are audible noise and the radio interferences are again caused because of the hardware, the corona or radio interferences are normally caused by the hardware, the conductors, the insulator hardware, the corona control rings. So, many of these metal parts in case if they are not in a smooth condition could create a noise, and this noise further travels in the conductors and will be a disturbance to the radio circuits. So, that is the reason where the minimum noise generated by the samples have to be mandatory as per the 400 or 765 kV levels. Typically 55 or a 56 decibel noise is the allowed for a transmission system. For a radio interference of 400 kilovolts and above, 1000 microvolts or 56 dB is the tolerable limits, and it should not increase more than 60 dB, that is 1000 microvolts is very important. So, these conditions have to be considered for the design of the conductors or the hardware which are being used for the towers. So, finally, the compensation requirement for the voltage control is again a factor under steady state which is to be considered for design of the extra high voltage or the ultra high voltage transmission lines for the tower configurations. So, this again I repeat the table which is shown, which gives important information about the nominal system voltages and the maximum system voltages where the equipment is designed, the insulation aspect is considered and designed. So, for 220 kV typically 245 is the maximum operating voltage of that equipment or the insulating system. Similarly, for 345 it is 360 and 400 it is 420. So, in India we follow 220 and 400 kV transmission, then further 765 and 1200 is in experimental stage. So, this gives the idea what is a normal operating or a nominal operating system voltage and the maximum voltage where the equipment has to be designed for that voltage level. So, how the power handling capability with reference to a single circuit, an example is considered here. So, the power handling capability of a single circuit, that is one tower consisting of 3 conductors RYB phase in a single tower, the power handling capability is given by the empirical formula which is given here, P is equal to 0.5 V square by Lx. This is in terms of megawatt per circuit. Again, if it is a single circuit it will be megawatt per circuit, where V is in kilovolts, L is the line length in kilometers, and X being the total series reactance per kilometer per phase. So, very important. This is the simplest formula where you can estimate the power handling capability either for a single or a double, or again there is a changes in case if it is a double circuit. This formula is for the single circuit power handling capability. So, here the percentage power loss, the total percentage power loss P is defined as 50 R by X. So, where R is the line resistance per kilometer per phase. So, if you consider 1200 kV circuit can carry as much as power usually for a 765 line. So, going in for higher the transmission voltage, earlier also we have discussed how much beneficial is going in for 765 to 1200. So, you can see the transmission could be improved 3 times using a 1200 kV of the 765 kV lines, and it will be 12 times of the 400 lines of the same distance of transmission. So, that is the advantage of going in for the higher the voltage, the power transmitted will be very high. So, the current density normally encountered lies between anywhere between 0.75 amperes per millimeter square to 1 ampere per millimeter square. These are some of the information to be known for the power handling and the power loss component of the transmission system. So, how the corona inception gradient, that is the corona inception, or there are two factors here, corona inception from the conductors which could be depending upon the diameter of the conductor. So, here there is a standard peaks formula, a well known formula for the calculation of the estimation of the corona inception gradient, which is given as 2140 into m into delta, the whole into 1 plus 0.031 divided by square root of r into delta, which is in kV per meter. The value will be in RMS, it is not peak, it is in RMS. So, here it is very clear, very simple formula which gives where m factor is the conductor surface roughness. So, the conductor surface roughness identifies whether the conductor is damaged, the conductor has projections, or the conductor is smooth. So, the surface roughness factor should be less than 1. So, usually 0.9 or 0.6 is considered for the normal case, 0.9 for wet conditions or the surface rain conditions, roughness is considered. Delta is the air density factor, again air density factor is given by B multiplied by 273 plus T0 divided by 1013 273 plus T, where very clearly it is defined R being the conductor radius in meters, B is the pressure in millibars, T being the temperature in degree centigrade, and T naught being the reference temperature. So, usually standard temperature as per STP, standard temperature and pressure conditions, 20 degrees is being used as a reference temperature. This is again planned to be considered in the revised standards 27, maybe in future in case of this value is adopted, the reference temperature could be 27, presently as per the standards it is 20 degree centigrade, which is taken as a reference temperature. So, the barometer pressure varies again with elevation, and the temperature drops by 10 millibars for every 100 meters. This is approximately increase in the elevation. So, the temperature correction is insignificant depending upon the area. So, the value of m, whatever the conductor surface roughness which I was mentioning here should be less than 1, is generally chosen, value of m is chosen to be 0.7 to 0.8 in case of clean weather condition, that is a fair weather what we call normal condition, no rain, no fog, dry conditions, and it is assumed to be 0.55 to 0.65 in case of fog, rain, or in the foul weather conditions. So, these are the calculations to be used, or the formula which is used for the calculation of corona inception for the conductors which are being used for the transmission lines. So, how the clearances are important? Now, the conductor to tower, conductor to ground, then conductor to conductor clearances are very important in the tower, any tower configuration. So, these play a role for various aspects, and these clearances have to be considered not only for the electrical clearances. Apart from electrical clearances, we have to look into the surges which earlier discussed, like the lightning surges, the switching surges, and the power frequency, over voltage, and the environmental conditions. So, the clearances are very important. So, while estimating the clearances for the conductor from the insulator string, that is the conductors to the tower clearances, conductor to ground and conductor to conductor are very important, and utmost consideration have to be done and proper calculations have to be carried out. So, conductor to tower, how it is done? It is given by a simple formula where V50 is equal to 1.3 into V50 for rod plane type of arrangement, which is equivalent to 650, where D to the power of 0.6. For this case, the gap factor is not generally assumed to be 1.3, and for conductor to conductor H is equivalent to 4.3 plus 1.4 d being in distance in meters. For face to face clearances, this is also described by a gap factor. Face to face, what you call one conductor to the other conductor, phase conductors, 3 conductors in a single circuit or 6 conductors in a double circuit, so on. So, the conductor to conductor or the face to face clearances is also sometimes described as a gap factor, whose value is 1.8. So, V50 is 900 d to the power of 0.6. So, conductor to tower, what is the clearances? This is given d is equal to V50 by 650 to the power of 1.667 meters, where V50 is equal to Vw by 1 minus 3 sigma, which is equal to Vw by 0.85 kV, and Vw is equal to withstand voltage. So, withstand voltage of that gap or clearance is Vw, which is further equal to Vw is equal to Ks into crest. Crest is peak line to ground voltage of the system. So, finally, the switching surge magnitude B, whatever the factor Ks per unit. So, this has to be clearly understood for the clearances while estimating for various voltage levels and various tower configurations. So, what is the air gap which is required to be maintained? That was for the switching surges which we looked here. These formulae are for the switching surges. For case of power frequency and lightning aspects, so the minimum clearances have to be adhered is for the power frequency V50 is 652 into D to the power of 0.576 kV. Crest is the peak, and for lightning it is V50 is equal to 500 D kilovolts peak. So, these are the important prescribed formulae while estimating the air gap clearances for the power frequency, lightning or the switching related surges for various tower configurations.